Hello everyone, this is a lecture video for Math 110 Intro to Number Theory, and we are going to talk about the problem of finding square roots modulo a prime p. So let's recall some terminology. So c, an integer, is called a quadratic residue modulo m, where m is an integer, if the equation x squared is congruent to c mod m has a solution. So in other words, when c has a square root modulo m. And just formally, there exists a b such that b squared is congruent to c, so namely there's a solution, and the values of b that solve this are the square roots. And otherwise we say that c is a quadratic non-residue modulo m. So just some notation that we've been using is that the square root of c plus or minus denotes the square roots of c modulo a prime p, because in the theory we've seen, x squared congruent to c has 0, 1, or 2 solutions. It has 0 solutions, of course, when it's a quadratic non-residue. It has 1 solution, as it turns out, when c is congruent to 0, and it has 2 solutions for non-zero quadratic residues. So that's just some notation that we've used in this case. And also, we're going to focus on odd primes, because when p is 2, this whole problem is trivial. 0 and 1 both have square roots. So we'll focus on odd primes. So first, let's consider an inefficient algorithm. So the most inefficient algorithm is that to calculate the square root of c, we take every value of b from 0 through p minus 1, square it mod p, and see if we get c. But, that is a lot of numbers potentially to check. But it will get the job done. So let's consider a small improvement just for the sake of exercising our understanding of quadratic, or of square roots and such. So since whenever b is a square root of c, the negative b is a square root of c, that means that we can consider the fact that between every pair of numbers here, so 1 and p minus 1, which is negative 1, and 2 and p minus 2, which is congruent to minus 2, we only need to actually check one of each pair. So that's the small improvement. We only have to consider half of the possible b's. So here's an algorithm. For each b in the range 0 through p minus 1 over 2, and this is the only reason we're, I guess, really needing p to be odd in this particular algorithm, so that's an integer. When we calculate b squared, check its c, mod p, and then if so, then the answer is b and minus b, or p minus b. And otherwise, if that fails, the answer is the empty set. Okay, so that's our algorithm. Let's see what that looks like in Python. It's a very simple piece of code. So it's a function that I've called naive square root. So, it's a little bit less naive than fully naive, but as we'll see, there's a much faster algorithm. And it takes the number c and also the prime p, and it assumes that the user of this function has actually ensured that p is an odd prime. Though actually this algorithm doesn't require it to be an odd prime. It can just be actually any number. And all it does is it returns, okay, so for each b in the range from 0 to, until p minus 1 over 2, but in Python, ranges go to 1 less than the number, so I had to add 1 to it. It checks to see if b squared minus c mod p is 0. And if so, that means that b is the square root of c, and we can return b as a square root. And otherwise, I just had it return none, just to signal that there is no solution. So, for example, naive square root 2 and 7, it returns 3, and 3 times 3 mod 7 is 2, so it's a square root. Or for a larger example, getting the square root of 2 modulo, I think this is the 10,000th prime number, something like that. Well, it gives it, and Python also has this nice function, which is taking a number, raising it to a power modulo another number. So it's actually doing, 5982 to the power of 2 modulo whatever the other number is. And so it's 2. Great. And for sake of seeing exactly how slow this is, I've taken, I think, the 100,000th prime. I'm not really remembering. Oh, the millionth prime. Yeah, okay, so let's look at the square root of 2 mod the millionth prime. And that took 1.5 seconds. So, if it's slow for a computer, it's probably impossible to do by hand, this algorithm. Though I think if you spend a couple of years, you could probably do it. Okay, so with that said, let's talk about a fancier algorithm that can actually be carried out by hand. It's more complicated though, but if you have these large moduli, maybe it's good to have, though usually this is just implemented for you already in a library. So anyway, the Tonelli algorithm. So what we're going to do is just lay some of the groundwork for what goes into it in theory, and then we'll see how it all comes together to make the algorithm. So the first bit is, given our odd prime p, then p minus 1 is some even number. And so what we can do is let's let L be the ord, the 2 ord of p, and let's let Q be, not of p, I mean of p minus 1. And so once we've got that 2 ord, we can then take p minus 1 and divide it by 2 to the L to get Q, to get this odd number Q. So then what we'll do is define some sets that we'll characterize in a bit. But so it's S0 through SL, and S0 is all the it's representative residues of mod p that are non-zero. So 1 through p minus 1. And then for each I that's less than L, we have the next set be all the squares of the previous set. So S0 is just the numbers, S1 is the squares of S0, S2 is the squares of S1, and so on. So let's look at a couple examples. So mod 7. So 7 minus 1 is 2 to the 1 times 3. So L is 1 and Q is 3 for 7. S0 is just 1 through 6. And then I went ahead and squared them all mod 7, and I got 1, 2, and 4. So those are our 2 sets. And something that we are going to look at for how to organize this is that we're going to, and we'll see this in the next slide too, but I figured I would draw it here. So, so what squares to 1? Well, 1 does, and 6 does. And what squares to 2? 4 does, and, well, let's see. So 3 squared, yeah, that's 2. And what's left? 5. Let's see, 5 squared is 25, which is 4 mod 7. So the idea here is that these 3 numbers up there, that is S0, and all of these, I meant to draw some dots. We're labeling, making this graph. So now, and that went out of frame. Okay. So the idea is, oh, and I got the indices backwards. Let's fix that before I say what the idea is. So what the idea is that S0 is all the dots, and then, and each dot, the relationship is that it's the squaring relation. And so we'll get these levels where removing the lowest layer, we get S1, then removing the next layer, we get S2, and so on. But at the very top layer, everything is just very loopy. All arrows just stay in that layer. Okay, so this is a 2-layer situation. Now let's look at mod 13. 13 minus 1 is 2 squared times 3. So L, in this case, is 2, and Q is 3. And so, again, S0, it's just 1 through 12. S1, I squared them all, so those are the quadratic residues. And S2 are the squares of the squares. Yeah, so by the way, everything that is in S0 but not in S1 are quadratic non-residues. And everything from this point onward is a quadratic residue. And also there's this relationship, which is that S0 contains, actually it strictly contains S1, which strictly contains S2. That's these sets that we're making. Okay, so again, I took all the numbers, squared them all, and put them at the level, put each number at the level that's sort of associated with the number. So 5, 8, 2, 11, 6, and 7, those are in S0 but not in S1. 12, 4, and 10 are in S1 but not in S2. And then 1, 3, and 9 are the elements of S2. So the very bottom layer, those are all the quadratic non-residues. There are no numbers that square to them. And then from the S1 layer and above, those are all things that have an arrow going to them. And something that's going to be a big deal is that once you're in the top layer, the SL layer, then to do square roots, you just have to actually square it a number of times. And then eventually, because eventually you'll get back to the same number by squaring something repeatedly once you're up here, then you can extract the square root, or one of the square roots. And what's also going to be important is finding some non-residue down here that will help us, push a number up to a particular level and reverse it. We're not going to go into that intuition, but so just to summarize a couple of those ideas that we've seen, S1 is the quadratic residues except for 0, and that's exactly what they are. And S0 minus S1, so the set minus everything that's in S0 that's not in S1, those are the quadratic non-residues. Also, something we can work out is that since SI is the squares of the squares of the squares of the squares, we can just collapse that whole thing down so it's not a recursive definition. And so SI is x to the 2 to the I mod p for all x in the range 1 through p minus 1. So now here's a place that primitive roots will help us analyze what this set even is. So let's let G be a primitive root mod P, which we showed existed a couple weeks ago in live lecture. And SI then is, because primitive roots enumerate all the non-zero numbers mod P by taking G to the 0, G to the 1, G to the 2, and so on. So by instead ranging over all x in the range 1 through p minus 1, we can range over all exponents k from 0 up to but not including p minus 1 of g to the k of the same thing. And that's mod p. So then, by exponentiation laws, that's just g to the 2 to the ik, 2 to the ik mod p. So keep that in mind, that's going to be useful. Let's look at mod 13 again to see what's going on. So 2 happens to be a primitive root mod 13, and so I've got the power wheel here of all the powers of 2 going all the way around, which shows us that we get 1, 2, 3, 4, 5, 6, 7, and so on. So S0, it's just by definition everything. So I've highlighted it all in magenta. S1, it's all the squares, and it turns out to be every other number, which makes sense because, as we saw, S1 would be g to the 2k, so it's all the even powers. And then S2, we can see it's every fourth element, and And you know it's g to the 2 to the 2k, so g to the 4k every fourth element. Yeah, so also si plus 1 is every other element of si. And that's one way to think about it. We're just dropping off them. You know, it's like this mesh where things are falling. Every other tine is falling off. Okay. So one part that's important here is we want to know how many elements are in Si. And like basically we know why already. It's that we're taking every 2 to the ith element. So if we divide by 2 to the I, that gives us how many elements there are. But I'll just do it you know, completely symbolically here. So we've already established that Si is g to the 2 to the ik, mod p for all k in that range. And so this proof rests on this claim that if 2 elements of this set are a congruent mod p, then the k and j that are being iterated over are congruent mod p minus 1 over 2 to the I, and vice versa. So this congruence is equivalent to that congruence. And we'll see why this entails what we need. So by Fermat's little theorem, the left-hand side of this equivalence is equivalent to, well, we can just take the exponents because it's mod up prime and g is a primitive root, so these numbers are coprime to p. So we can just look at the exponents, mod phi of p, which is p minus 1. And then, okay, so we've taken what we were trying to show, replaced it with this. And this is true since, well, 2 to the I divides everything in sight here. So as we learned in our study of linear equations and stuff like that, and also just the definition of modulo, we can just divide everything by 2 to the I. So, and that gives you an equivalent equation, or a congruence. So these are just equivalent. Okay, so the claim is set. So what that means is that, first of all, if we have an element in here, we can take its k and reduce it mod p minus 1 over 2 to the I. So we actually only need to range over that. And secondly, if we have 2 of these k's that are inside that inside this range, then well, then they're congruent mod this modulus. So we can describe Si as this set and also say that there are no repeats. So there's no pairs of k that give the same number. And so that means, well, p minus 1 over 2 to the I is the number of elements in Si. Yeah, so this gives credence to the observation that every time I increases, then Si will have half as many elements as the previous. And one corollary here is that since L is the largest number that we can divide by, our largest number so that 2 to it is something we can divide by, that means that SL is odd. So that's one reason why we stopped there. Okay, the next thing that we need for the Tonelli algorithm is being able to do some sort of membership test. We want to have some way of knowing whether a given element is actually in Si. So let's say X is in S0, and I is one of the indices that are valid. Then X is in Si if and only if X raised to this power, p minus 1 over 2 to the I, is congruent to 1 mod p. And since it's reasonably efficient to compute exponents mod p, because we can do that like repeated square thing for X to represent the exponent, I guess in base 2. And yeah, so then this means that we actually have a way of telling whether X is in Si. Short of enumerating every element, you know, if we didn't know this fact, we'd probably have to repeatedly square everything mod p and see if x happens to be among the ith iterated squares. And that's not a good situation if you want to compute fast. So let's recall that SI can be put in this form in terms of a primitive root g. And then let's break this into two parts, the forward direction and the backward direction for the if. So for the forward direction, let's suppose that x is in SI, and then let's let k be the number such that x is congruent to g to the 2ik. That comes from x being in SI written this way. So once we've written x in that form, we can check that when we raise it to this p minus 1 over 2 to the ith power, then the 2 to the i's cancel out, and we can bring the p minus 1 in. And actually, we didn't even need to cancel them out. All that really matters is that there's a... we want to cancel them out so that we see that we have g to the p minus 1 to some integer power. But since g is a primitive root, well, actually, just Fermat's little theorem, that's 1 to the k, which is 1 mod p. So definitely things in the set satisfy this condition. But what about the converse? So let's suppose that x satisfies this condition. And so now, just thinking about this as a polynomial congruence, we've got x to some power is 1 mod p. And in live lecture, we showed that we showed that x to the d congruent to 1 mod p if has d solutions, like exactly d solutions, if d divides p minus 1. So, well, p minus 1 over 2 to the I, that's a divisor of p minus 1. So it has exactly that many solutions because, well, as I said, it's a divisor of p minus 1. So SI consists of solutions to this by the forward direction, SI consists of solutions to this equation, and also every solution has to be in that set because by the previous lemma we calculated the cardinality. We have exactly the number of things that we thought we had, so we've characterized them. And that's that lemma. Okay, now we've got all these sets, and you're wondering what are they all for? Well, one of the things that's useful here is that in SL, the very top where I said everything's all loopy, square roots are easy. And the way I'll do that, argue that for you, is just show I can write a square root down and not really think about it too hard beyond that. So let's C be in SL, and then because it's in SL by our previous lemma, by our previous characterization of SL, we know that there's some k from 0 through q, where q, remember, is the quotient of p minus 1 by 2 to the l. And so c is g to the 2 to the l k. So we can write, and this is mod p. So we can write c in this way. And now let's notice that if we take c to the q plus 1 over 2, a very specific exponent, and square it, we get c. So let's just run through that. So doing some exponent manipulation, this squared is c to the q plus 1, which is c times c to the q. And then c, we said, was of this form, so we can plug it in for the second one. And then rearrange the exponents to get c times g to the 2l, 2 to the lq to the k. And because 2 to the lq is p minus 1, and g has, well, Fermat's little theorem, that's 1. So we got it's congruent to c mod p. that means this is a valid square root. And so the square roots are plus or minus that. And that's convenient to know that we can just get them. But okay, so that's SL. This only helps us if p minus 1, let's see. Oh yeah, this only helps if p minus 1 over 2 is odd for solving for those primes. But we want to do this for square roots in general. So let's analyze something, or well, yeah, we're going to analyze this particular situation given some particular data. So let's just suppose n is any quadratic non-residue whatsoever. And there's a reason for using quadratic non-residue, and hopefully it will be clear a bit later. But if we have one, then the idea is we want to find an even exponent e such that n to the minus e c is congruent to p, or mod p is an SL. So yeah, so there always will be some there always will be some exponent that will cause this product to be an CL. But what's more, we can make sure that it's even. And then, because it's an SL, we can compute some square root of it based on the previous slide. And so we can use as our square root n to the e over 2, which we can calculate because e is even, and multiply that by a. And so, well, if we look at it, if we squared this, then we get n to the e times n to the minus e c, and the n to the e's cancel out. So that would give us a square root. And, you know, it would actually be plus or minus to get both of them. Okay, so how do we find this e? And this is also, I guess, a way to prove that an e even exists. So to do it, we do it in a step-by-step way, walking down these nested SI sets. So we start with E0 is 0. And we can see that n to the minus 0 times c mod p is an S0. But that's because S0 contains everything. But, you know, E0 is even, and that's important. So now, the next thing is, given that we know that we've found an EI where the condition is satisfied at the SI level, we want to find the next EI plus 1 such that that satisfies it as at the SI plus 1 level. So the important thing here is that either the same value or the same value but plus 2 to the I is guaranteed to work. And since I in this case is we actually are gonna, well, we'll see. We only ever deal with I as 2 or more, because if our number starts in S0 but not in S1, then it doesn't have a square root. So we should actually be starting at 1 here, just to make this work a little better. Okay, so yeah, so then since I is 1, then it remains even. That's just why I wanted to make sure. So since we can write C as, so I'm going to show you that this does work. So we can write C as a power of G mod P. And we can also, because n is a non-residue, write it as G to the 2m plus 1. Because remember, non-residue means that it's in S0 but not in S1. And that means that the exponent to G is odd. So m is a number, and k is a number, just arbitrary, so that we've written C and n in this way. And let's assume that it works at the SI level. So now let's calculate the exponent here. So the exponent well, so this is g to the 2m plus 1 to the minus e I times g to the k. And so if we collect all the exponents, we get this expression here. And as we've established, elements of s to the I are powers of g whose exponent is divisible by 2 to the I. So we get this equation, or this divisibility relation, which, you know, you can also think about this as a saying that the right-hand side is congruent to 0 mod 2 to the I. So if we increase I by 1, then there are two things that can happen. Either this thing is congruent to 0, or it's congruent to 2 to the I. And that's mod 2 to the I plus 1. And this is just because, well, which numbers are, if you have a number that's 0 mod 2 to the I, what are the possibilities mod 2 to the I plus 1? That's a little exercise. So if it were actually the case that's, okay, so if it's 0, then 2 to the I plus 1 divides the left-hand side here. And so then I plus 1 could just be EI, and that would work. But let's say it's not 0, and then instead 2 to the I. Then what we can calculate is that if we add 2 to the I to EI and run through everything here, then let's see. So there's this 2 to the I times 2 in there. That will cancel out mod 2 to the I plus 1. And then also we have then there's this 2 to the I times 1, which will give us a 2 to the I, which will perfectly cancel out the remaining this expression, after we multiply it all out. So anyway, you can run through that algebra if you need some convincing. So so this is how we can recursively compute our E, because then we use E equals EL after going step by step in this way. Okay, so putting it all together, here's like a more step-by-step way of explaining it. So given a non-zero integer, well, actually, non-zero is not quite right. We want it to be a number that is, well, let's just fix. I remember that there is a little error here, and I can just fix it right now. So if C is congruent to 0 mod P, the answer is just the set containing 0. So after this point, we can assume C is non-zero, mod P. Okay, so then if C is not an S1, namely C is a, right, I forgot one more thing here. We want to check. So C is just any integer. We need to reduce this mod P. Okay, so if C mod P is not an S1, that means C is a quadratic non-residue, which means it has no square root, so we can just answer with the empty set. So then we continue with L and Q defined like the discussion so far. And then we have N be some arbitrary quadratic non-residue, mod P. And so this is a random part of the algorithm. It turns out that there's no real good way to find a quadratic non-residue in a deterministic way, but you can choose numbers randomly mod P, and there's a 50-50 chance that it's a quadratic non-residue. And so to check whether it is or not, we check to see whether N is not an S1, which is something that we know how to compute. And so we just do that. On average, it will take 2 iterations and we'll get 1. So then now we compute E. So we start with e is 0, and then for each I in 2, 3, and so on, our assumption is that n to the minus ec mod p is in si minus 1. But what if it's not in si? Then, as we discussed, we can add 2 to the I minus 1 to e to get an e where this would be satisfied. Right, so then at the end of this checking through all the different i's, then what we have is that indeed some even power of n times c mod p is in SL. So we use our formula that we found to compute the square root of that element mod p in the fast way, and then we multiply it by n to the e over 2, and this then gives us a square root of c. And then to get both square roots, we do minus b. So we return both of those square roots. So that's the Tonelli square root algorithm, and it's not so hard to implement in Python. Sure, it's a number of lines. About a third of them are comments. So one aspect is x in SI? That is one calculation, and that's mod p. And so for that we calculate x to the power of so here's a little trick in Python. This is the division by a power of 2 operator. So this is p minus 1 over 2 to the I. Just happens to be sort of fast. So so we do x to the power of this expression that we've already determined works for membership, mod p, check to see if we get 1. If we do, then it's an element. Okay, so that's a useful little function for this. Then the main algorithm just walks through all the steps I already described. So let's see. One part is Python doesn't know about ORD, so I calculate it by repeatedly checking if q is even, and if it is, divide it by 2 and add 1 to L, and eventually it's odd. Also, this is the part that finds a quadratic non-residue. It chooses a random number, and then this could be 2 if we want, but it's not going to be really a measurable difference in speed. So so we check to see is n not in SI. So this is n not in SI, or S1. So that will, on average, run in 2 iterations. And then there is calculating the inverse, the multiplicative inverse of n, which we need to raise n to the minus e in those steps. So this is using Fermat's little theorem, that if you raise a number to the p minus 2 mod p, then you get a multiplicative inverse. It's not the fastest way to do it, but it works. And I didn't want to implement the GCD2 to calculate that. So then, this is the iterative part that calculates e, where it keeps checking to see is n inverse to the e mod p times c in SI mod p. And if it isn't, then it adds the 2 to the power of I minus 1. So then the rest is just, calculating the square root of that element that we know is an SL, using the formula from, from earlier. And then we multiply that by n to the e over 2. And that gives us the square root, or one of them, so we get 2. So just to test it out, so in this, the square root of 2 mod 7, it gives us 3 and 4. And then that one thing that took 1.5 seconds with the semi-naive algorithm took only 0.0001 second with this algorithm, which is 10,000 times faster. So hopefully that, shows you that going through all this effort of analyzing the structure of quadratic residues actually did something useful. Anyway, so that's this video, and I'll see you next time.